This question is from GATE 2015, Mechanical Engineering paper, set 3, question number 46. For the overhanging beam shown in the figure, the magnitude of maximum bending moment in kilonewton meter is dash. Now this is a determinate structure because we have two unknowns, the external reactions that support, let them be RA and RB. We have two equations of static equilibrium, summation of forces in vertical direction. Let this be the y-axis and this be the x-axis. So summation of forces in y direction is 0. This is the one equation, and summation of moment about points A and B is 0. So summation of moment is 0 is also a static equilibrium equation. So we have two unknowns, two equations. This structure is a determinate structure. In the first part, we will find out the unknown reaction RARB. First equation that we use is summation of forces in y direction is 0. Therefore, we can write downward uniformly distributed load of 10 kilonewton per meter intensity into the distance 4 meter. So the total load is 10 into 4 kilonewton downwards. That is why minus 20 kilonewton is the point load. So we do minus 20. There are two upward external reactions RA and RB. So we'll do plus RA plus RB is equal to 0. First equation that we get here is RA plus RB is equal to 40 plus 20, 60 kilonewton. To form the second relation between RA and RB, we can use summation of moment about support A is 0. Because this is a simple support, resisting moment here is 0. So if we take moment about point A, we'll get intensity of the UDL 10 kilonewton per meter into the distance 4 into distance from its CG to point A, that is 2 meters. So this distance is 2 meters. So we will assume the sign convention as sagging is positive. These are sagging moments, these are positive, and that is why when we are on the right side of the section, we are taking this moment from right side, clockwise is negative, anti-clockwise is positive, so clockwise is negative, hence we can do minus 10 into 4 into 2. This is one. Moment due to the point load 20 kilonewton will be 20 into distance 6 meters. This is also clockwise. So minus 20 into 6. Due to RB, there will be an anti-clockwise moment which will be positive RB into 4. So plus RB into 4 equal to 0. Let's solve this. We have RB is equal to 10 into 4 into 2, 80 plus 20 into 6, 120. So 80 plus 120 gives 200. 200 divided by 4 will give us 50 kilonewton. So we got RB as 50 kilonewton. We can find out RA now. RA will be 60 minus RB, that is 60 minus 50. Therefore, RA is 10 kilonewton. Let's write it here. RA is 10 kilonewton. Now in the second part, we'll try and find out the maximum moment. To find out the maximum moment, we'll draw the bending moment diagram. In order to draw a bending moment diagram, let's assume a section x dash at a distance x from the origin. We have already marked the axis in the previous diagram as y and x. Origin is at point A and x is taken from point A to the section xx dash. Again, let me write the sign convention here. So sagging here is positive. Writing the moment equation, we will have anti-clockwise negative on the left side. So minus of 10 is the intensity, but the expanse of this UDL is only x now. It is not 4, but it is x. So 10 into x into CG of this load spread for x distance will be x by 2. So it is minus 10 into x by 2. 10 kilonewton generates a clockwise moment on left side of the section. So this is positive. That is why we write this as plus 10 into distance x. So mxx dash comes out to be 10x minus 10x square by 2, which is 10x minus 5x square. Now by putting the values of x, we can find out the moment at particular points. At x equal to 0, clearly it is 0. We already took it 0. Now first thing, let's find out the moment at B. Because at A, anyway the moment is 0. At C also, there is no moment resisting support, and that is why this will be also 0. At free end also moment will be 0. So at B, that is x equal to 4, we can find out the moment at B is equal to, by putting x equal to 4, we have 10 into 4 minus 5 into 4 square. This comes out to be minus 40 kilonewton meter. So we have a value of minus 40 kilonewton meter at B. At C it is 0. So we can draw this part of the BMD here. Now we need to draw the rest of the BMD. Here beyond point B there is a UDL. So definitely the nature of bending moment diagram will not be linear here. And it should go back to 0 at A. Now we need to find out the maximum moment that will occur between A and B because of the UDL here. For that, we'll need to draw the shear force diagram so that we can see where the shear force is changing its sign. Wherever shear force changes its sign, moment will have a maximum value because we know that shear force is the slope of bending moment diagram. At maximum bending moment, slope will be 0 and that is why shear force will have to go to 0. Let's draw the shear force diagram now. Between A and B, there is a UDL. Definitely shear force will not be a constant value. It will be linearly increasing or decreasing. At A, we have 10 kilonewton upward shear. So we can draw it like this. This is 10. Also at point C, we are clear that there is a downward load of 20 kilonewton. This is 20. At B, we should have a total force of 50 kilonewton. So how can we represent it? Between B and C, there shouldn't be any load. It will remain constant value of 20 up till we reach B. And then at B, downward 20. And then to compensate for this 50 kilonewton, we need to add 30 more. So it will look something like this. Now from B to A, we can directly join with a line. Here at this point, shear force is changing sign from positive to negative and it is becoming 0 at this point. So definitely this is that point on bending moment diagram which will have the maximum bending moment. So this is the point on the beam which will have the maximum bending moment. How will we find this point? Let this distance be A. We know the total distance between A and B is 4. So this distance will be 4 minus A. By using similar triangles in these two triangles, this one and this one, we have the relation A by 10 is equal to 4 minus A by 30. Therefore, we have 4 minus A by A is 3. Rearranging this, we get the value of A as 1 meter. So this A is 1 meter. At 1 meter, whatever is the value of moment will give us the positive bending moment. Negative value we already have 40 kilonewton meter. We want to check whether the positive one is greater than 40. So by putting 1, we'll get moment at x equal to 1 meter is equal to 10 into 1 minus 5 into 1 square, which is nothing but 10 minus 5 kilonewton meter. So it will be a second degree curve and will look something like this, which will have a peak at 5 kilonewton meter. So among 40 and 5, 40 is the greater one, and although it has a nature of hogging, this is a hogging bending moment of 40 kilonewton meter, still it is the maximum. So the maximum bending moment in this loading condition for this given overhanging beam is 40 kilonewton meter. Let's go and mark it. The magnitude of maximum bending moment is 40 kilonewton meter. To learn more about bending moment in beams, you can refer to the NPTEL video lecture 12. Beams 3 from the course Engineering Mechanics. This course is by Professor K. Ramesh. He is from IIT Madras. I hope this solution will help you clear your doubt. Thank you.